Well, thank you very much, Shirshendu. It is a very nice introduction. I should first apologize for not being able to join you in Bangalore. I had some issues with my passport, which was not valid for long enough. So I had to cancel my visit. I'm very sorry for that. So despite that fact, so I will speak about Carleman estimate for the Laplace operator. And the lectures I will give is based on a lecture we give with Jérémy Dardet, first in, so Jérémy Dardet is in Toulouse, so we gave that lecture in Toulouse first, and then in China. So I hope you will find some nice informations there. And more or less, I will try to present it with a few hours without being too technical. So maybe at some point I will skip some details. If this is a problem for you to follow, then please interrupt, and I can try to give the details. Otherwise, most of the details should be in these lecture notes, which are available on Hub. Okay. So let me start. I will start with the Laplace operator in the strip. So basically what I will be considering here is a domain omega, which is of the form 0, 1 cross RD minus 1. Okay, so this is a vertical strip like this. And I will consider the problem Laplacian u equal to f in omega. So for this problem, as usual, you need to add some further information, so some boundary conditions. So again, omega here is the vertical strip. Okay, so I will discuss first the Cauchy problem. Maybe I will write problem. Okay, completely. So the Cauchy problem is the following. You assume that you have Laplacian u equal to f in omega, and you know u0 and x prime. So we'll call this one GD of x prime, as for, well, GD stands for Dirichlet. Okay, and D1U of 0 x prime equal to Gn x prime, so n stands for Neumann. So for x prime in Rd minus 1, okay, meaning that in what happens next, there is this convention that x in omega is written as x equal to x1 x prime, with x1 in 0, 1 and x prime in Rd minus 1. Okay, so this is the problem I want to consider. So here, maybe I will try to draw a picture. So I have my vertical strip, omega, and on the boundary, so here I have Laplacian u equal to f inside, and here I have two informations. So two informations on this boundary. I have the Dirichlet plus Neumann boundary conditions. Okay, and so the question is, can we recover U? Okay, so this is what is called the Cauchy problem or the Laplace operator. Cauchy problem. So when you have an equation like this, the first thing probably is to try to use the symmetry of the problem or the specific geometric setting of this problem. So here you see that, in fact, this is so this omega is a Cartesian product, right? It's 0, 1 cross RD minus 1. So it's very natural to try to do the Fourier transform in the x prime variable, right? So this is what we will be doing. So we introduce what I will call the partial Fourier transform, which is x prime gives psi prime. Okay, so for f in, let's say, L1 of the strip, I set f hat of x1 in psi prime equal to 1 over 2 pi d minus 1 over 2, let's say. So this is just a normalization of the Fourier transform, integral on Rd minus 1 of f x1 x prime exponential minus I x prime dot psi prime dx prime. Okay, so this holds for x1 0, 1 and for psi prime in Rd minus 1. Okay, so once you have the Fourier transform, so this is the partial Fourier transform, this is very helpful to understand what happens in the x prime direction, right? So let's put it that way. We have d11 plus the sum for g from 2 to d of dgg of u equals to f. Okay, so this is in the strip, so 0, 1 cross Rd minus 1. So after the Fourier transform, it will give you d11 minus psi prime square of u hat of x1 and psi prime equals to f hat of x1 and psi prime in 0, 1 cross Rd minus 1. And the boundary conditions will simply be u hat of 0 psi prime equal to gd psi prime and d1u hat of 0 psi prime equal to gn hat of psi prime. Okay, so these are the system. These equations are the system. Once you perform the Fourier transform in the x prime variable. So once you have that, you see it is much easier to deal with the equations because now this is a family of ODE of second order ODE in x1, okay, indexed by the Fourier coefficient, or by the Fourier parameter psi prime. Okay, so this I know how to solve, right? So we know how to solve. And so I can give you the answer. So again, this is, well, now this is an easy exercise, right? We have a parameter psi prime, it does not depend on x1. So we are really solving family of ODE. And at the end of the day, after a few computations, you will get a formula like this. So let me write it, trying not to do mistakes, but okay. Divided by psi prime. Okay. So basically, you see, given f, so given the source term, f, let's say that f could be in L2 of the domain, given GD and GN, so which will be the boundary condition. So probably if we know about trace theory, what would be very natural would be to have a GD in H3 half of RD minus 1 and Gn in H1 half of RD minus 1. Then the above formula gives the U. Okay, so this is a case in which we have what is called uniqueness in the Cauchy problem. The difficulty here, so there is a problem. What's the problem with that formula? So the problem is that this is in Fourier, right? So in principle, we'd like to have U defined in the physical space. But the difficulty here is that, so for instance, in cosine hyperbolic of psi prime x1, so in this term here, but in fact in all these terms, right? So maybe, well, I should remember that cos h of z is exponential z plus exponential minus z over 2. And well, hyperbolic sine is, I know that maybe the notation is not completely standard, so let me just write it somewhere. Sinus h of z is exponential z minus exponential minus z over 2. Okay, so the difficulty is that in those terms you have guys like exponential zeta prime x1. And you see for x1 positive, so it contains. Okay. But for x1 positive, this is something which does not belong to S prime. So the function psi prime gives exponential psi prime x1 does not belong to S prime of RD minus 1. So I cannot take the inverse Fourier transform of this. So I do not know how to take the inverse Fourier transform of such function. Okay, so this is a kind of a paradox, right? You have a very nice formula, but somehow it is useless because you cannot take the inverse Fourier transform of it, right? So this is typical of this Cauchy problem for the Laplace operator. So you have uniqueness, so a solution of Laplacian u equal to f in omega with u0 x prime equal to gd x prime and d1 u0 x prime equal to gn x prime for x prime in R d minus 1 is unique. Well, I should emphasize when it exists. Okay, but you do not have any reasonable, I would say, stability estimate or continuity estimate which to f, gd, and gn gives you. And so here, when I mean reasonable, I mean in Sobolev spaces. Okay. So, for instance, if you go to Gevrey class or something like that, you may have stability, but okay, it's something else. So reasonable here means in Sobolev spaces. Okay. So this is regarding the Cauchy problem. But then, I mean, there is another point I'd like to mention is what about the Laplace operator with Dirichlet boundary conditions? So here I am, I have again Laplacian u equal to f in omega, which is the strip still. I have u of 0 x prime equal g0 x prime, u1 x prime equal to g1 x prime. So for x prime in Rd minus 1. So this is a Cauchy problem. Well, this is, let's say, the usual elliptic problem where you have Dirichlet boundary conditions on the boundary. And so in this case, you know that it is well posed. So for f in L2 of omega, for G0 and G1 in H3 half of Rd minus 1, there exists a unique solution U in H2 of omega of the above problem. Solution of the above problem. Okay. So, well, this is known, and you see you have a kind of paradox because here you can still do the same thing. I mean, you can still do the same thing to compute the solution by looking at the Fourier transform. So you'll have d11 minus psi prime square of u hat of x1 psi prime equal to f hat of x1 psi prime, except that now you'll have boundary conditions at 0 and in 1. Okay, and so then, of course, you can still compute explicitly the formula. I can maybe show it to you, but probably that wouldn't be very interesting. But here, okay, maybe I will just write the beginning. Let's say u hat x1 psi prime will be g0 hat of psi prime, hyperbolic sine of 1 minus x1 psi prime divided by the hyperbolic sine of psi prime plus g1 hat of psi prime. Okay, so again, this is only a computation, right? So it's not very interesting. But what's interesting is to see the behavior of, so let's say when f hat equals to 0. Okay, what's interesting is to see the behavior of these two quantities here. And in particular, to realize that these two quantities are bounded uniformly in psi prime and x1. Let's say in x1 psi prime in 0, 1 cross RD minus 1. So this is why at the end you'll get a well-posed problem in the usual class. So in fact, if you track very precisely the dependence in psi prime and so on, you can recover by hand the usual theorem which is here. Okay. So this is, let's say, more or less classical stuff. But now what is Carleman estimate? So what's the idea? I will put with a linear weight because it's easier to understand at first. So the idea is to say, okay, I have a formula which gives me uniqueness with, from the information I have on the left, but it is not well posed. Okay, and I have another formula which gives me well posedness. Okay, when I have information on two sides. So can I try to interpolate between the two previous approach? And in order to do so, I will allow growing exponentials of the form exponential kx1. For k, a free parameter. So let's say that k will be in R, plus, and maybe k larger than 1, because at the end, I want to allow this parameter k to be large. I mean, otherwise comparing to exponential kx1 is like comparing to a constant if k is small. Okay. So in order to do so, again, I have here, I have Laplacian u equal to f in omega. And now I assume that I have three boundary conditions. So I have u0 x prime equal to something. I have u1 x prime equal to something, and d1 u0 x prime equal to something. So I will call this one gn of x prime. Okay, so you see I am in that setting. So here I have Laplacian u equal to f. Here I have Dirichlet plus Neumann boundary conditions. And here I have only Dirichlet. So somehow these two correspond to the first case. Okay, to the Cauchy problem. Okay, and these two correspond to the second case where it is well put. Where you have well posedness. Okay. And so we want to interpolate. So what we will do is simply look at u of x exponential kx1 and try to get estimate on this. Okay? And try to get estimates. So I will call this v of x to get estimates on v uniformly with respect to k. Okay, just one remark before going further is that here I have three boundary conditions. Three boundary conditions for the Laplace operator, this is too much. So this means that there are compatibility conditions between the three. There are compatibility conditions between G0, G1, Gn, and F. Okay? So I'm not claiming that for any F, G0, G1, and Gn there exists a U. Okay? This is not what I'm doing. What I am doing is saying that if I have a U which satisfies the above system, then I can get some estimates. Okay? So somehow this formulation encodes that there are compatibility conditions between all the data. Okay? So now I'm trying to get estimates. So I don't know if you still see this. So trying to get estimates on here. So I fix k larger than 1. I set v as u of x exponential kx1. I set, let me just check. I will try to keep the same notations. I will set capital F Sorry. So capital F of x equal f of x exponential kx1. So in 0, the conditions will be more or less the same. So let me write the equation. So what is the equation satisfied by V? Is, so this is a simple computation, right? V of x equal U of x exponential k minus 1. So you just write that Laplacian U equals to F. This is equivalent to say that Laplacian of V of x exponential minus kx1 equal to f of x exponential minus kx1. And then you develop the computations, and at the end of the day, you will have that d1 minus k squared plus Laplacian prime of v equals to f, okay, in omega. So here again, omega is the strip, right? Laplacian prime is the Laplace operator in the x prime coordinates. V of 0 x prime, this is simply g, this is simply u 0 x prime, so this is g0 of x prime. V1 x prime, it's u1 x prime exponential k. So here this is g1 So I put it with a plus, but I wanted to put a minus. I'm very sorry about that. So I want to compare with exponential plus kx1. So I will divide u by exponential kx1. So it means that v is u exponential minus kx1. So it means that here I have a minus, here I have a minus as well. So here it goes with a plus. And here it goes with a minus. This is better. And d1 v of 0 x prime, this is d1 u of 0 x prime minus k of u 0 x prime. So this is gn x prime minus k g 0 x prime. Okay, so it's only a change of a known, right? But here the good thing is that, so this is known, right? This is known, this is known, and this is known, right? So we know all the boundary conditions, we know the source term, and we want to recover V. Okay, so can we do that? And of course, the answer will be yes. And so the trick will be the same as usual. So we will do a Fourier transform. In the x prime variable, right? And this will give the following family of ODE, d1 plus k squared minus psi prime squared of v hat okay, get v hat 0 psi prime equal to g0 hat of psi prime, v hat 1 psi prime equal to g1 hat psi prime exponential minus k, d1 v hat of 0 psi prime equal to gn hat of psi prime minus k G0 hat, etc. Okay? And you see, once you have this, in fact, you know that you will be able to get estimates for a simple reason. So the reason is that this is a family of ODE, again, of ODE indexed by psi prime, so the Fourier parameter in RD minus. Okay, so given psi prime, you know exactly how to solve this equation. Okay, so let me give you the result we'd like to prove, and then I will try to prove it in a few steps. So the result, so it's a theorem. So for simplicity, I will do that with G0 hat equal to 0 and G1 hat equal to 0. Okay, but I will state it in first in U. Okay, so there exists a constant C positive such that for all K larger than 1, any function U, so for all U in H2 intersected H10 of omega, we have K square norm of U exponential minus kx1 in L2 of omega square plus gradient of U times exponential minus kx1 in L2 of omega square is less than a constant times Laplacian U exponential minus kx1 L2 of omega square plus constant k, the norm of Gn. So Gn is the norm I'm traced, right? So it's D1 U0. And here we can put L2 of RD minus 1. Okay, so this is what I call a Carleman estimate. With a linear weight function so the weight, by definition, is the function which is here. Okay, so you see it will appear in each terms, right? So here I could write exponential minus k times 0 in the last term, but it doesn't, well, it is 1, so I just remove it. Okay, so the weight function is x gives x1 or minus x1 in here. And what matters, so what is important in Carleman estimate is, what matters is the dependence with respect to the Carleman parameter k. Okay, so you see here this constant c does not depend on k. Okay, so we have this weight function exponential minus kx1, which somehow twists the usual norms. Okay, and then you have this dependence here in k, but you know explicitly how everything depends on k. Okay, and this is true again. So there is a constant c, one constant, such that for all k large enough, we have this estimate. Okay. So, well, I will first prove it, and then I will show you what applications it has. But let me mention that it is quite powerful tool, and this will be the goal of the lecture. So let me go to the proof. So see what we did before. So we have u in h1, 0 of omega intersected with h2. So then we set v equal to exponential minus kx1 times u. We set f equal, or capital F equal to Laplacian u exponential minus kx1. We set gn equal d1u 0. Okay, and we are in the previous setting. So we had at the end d11 minus k. No, sorry, it's with a plus, right? It was with a plus, yes. Minus psi prime square of v hat of x1 xi prime equal to f hat of x1 xi prime. And then you get v hat of 0 psi prime equal to v hat of 1 psi prime equal to 0. This is because here I have imposed homogeneous direct boundary condition, but of course, I mean, if you want to track precisely what happens with non-homogeneous direct boundary condition, you have everything above to do that. And you have that d1 v hat of psi prime is gn hat of psi prime. Okay, so then to get estimates on such a thing, so there are many ways, but one I like is to realize that our operator d1 plus k square minus psi prime square, this is the product of two operators which are explicit. Okay, and so you can introduce a function w that I will call w hat of x1 and psi prime, which is simply d1 plus k minus psi prime of v hat of x1 psi prime. And the system, the previous equations, now, sorry, now with d1 plus k plus psi prime of w hat equals to f hat, w hat of 0 psi prime equal to gn hat of psi prime, and d1 plus k minus psi prime of v hat equals w hat, and v hat of 0 psi prime equal to v hat 1 psi prime equal to 0. So this is in omega. This is for psi prime rd minus 1. And so here when I'm writing in omega, I'm meaning for x1 in 0, 1, and psi prime in R dimension. Okay. Okay, so then to get estimates, you see it's about getting estimates on ODE, which can be solved explicitly, right? So each of these ODE can be solved explicitly with formula, but in fact, what we want is estimates. So to get estimates, there is one very useful thing, which is simply a kind of multiplier technique. So to get estimates, so you will start with W hat, okay? So you will have estimates on W hat in terms of F hat and G and hat. And then you'll get estimates on V hat in terms of W hat. So this is a kind of cascade argument, okay? So to get estimates on W hat, what you do is simply take the square of this equation. So you do all the computations with psi prime fixed, okay? Because this is an ODE in psi prime. So we fix psi prime and do the computations with psi prime fixed. So you see you'll have something like that. So this equals to D1 plus K plus psi prime D1 W hat plus K plus psi prime W hat square dx1. So this is in 0, 1. So this equals the integral for x1 in 0, 1 of D1 W hat plus K plus modulus of psi prime square W hat x1 psi prime square plus, so there is a cross product, right, which will be 2k plus psi prime times the real part of d1 w hat bar dx1. And then, of course, you will do one integration by parts, because this guy here is d1 of w hat square over 2. And so you'll get that this is the integral over x1 of d1 w hat x1 psi prime plus k plus psi prime square w hat of x1 psi prime square plus, so this is dx1, plus k plus psi prime of w hat of 1 psi prime square minus k plus psi prime of w hat of 0 psi prime square. And that's it. So you end up with k plus psi prime square integral over x1 of w hat x1 psi prime square less than the integral, so x1 is in 0, 1, of f hat x1 psi prime square x1 plus k plus psi prime of w hat. Okay. So here you see this is an easy computation, multiplier type argument somehow, where you get immediately an estimate on w hat in terms of the informations you have. So remember that this guy W hat here is Gn hat of psi prime. Okay, so we have informations on F and W in x1 equal to 0. And with that, we estimate everything in a very reasonable Sobolev space. Okay, so then you should get estimates on V. So in order to do that, you do the same. So remember that you have an equation like this, D1 plus K minus psi prime of V hat equal to W hat. Okay, and you have two boundary conditions, V1 of 0 psi prime equal to V1 of 1 psi prime equal to 0. So in fact, again, you have some kind of compatibility conditions on W hat to guarantee that you have the existence of a solution to this equation, right? But then to get estimate, you simply take the square of both sides, okay, and integrate in x1. You get that this is d1 v hat. So I'm going slightly faster maybe. So this is d1 plus k minus psi prime of v hat square dx1. So this is the integral from 0 to 1 of d1 v hat x1 psi prime square plus k minus psi prime square v hat x1 psi prime. And then again, you have a cross product, right, which would be the integral from 0 to 1 of k minus psi prime times d1 of v hat square dx1. And this is, of course, k minus psi prime of v hat 1 psi prime square minus v hat of 0 psi prime. And with the above conditions on v hat at 0 and v hat in 1, this is 0. Okay, this one is 0, this one is 0. I just want to comment 1 minute this term here. So in these boundary terms, you see where the informations come from, right? So let me explain. So imagine that you have non-homogeneous Dirichlet boundary condition, so that v hat and at 1 or and 0 is non-zero. Then you see that, in fact, the sign of k minus psi prime will tell you which one of the information on the boundary should be considered. Okay? So in particular, when psi prime is less than k, so you have k minus psi prime is positive. So if you want informations on v hat, you should use information on v hat 0 psi prime is the important one. So it means that for low frequencies, in fact, the computation you are doing is very close to the case of the Cauchy problem, where you are going to use both informations in x1 equal to 0. Okay, so this is close to the Cauchy problem. When psi prime is larger than k, you see the sign of k minus psi prime will change. So this is a high frequency regime. And then to get a stable estimate, what you should use is the information on on V hat 1 psi prime allows to get a stable estimate. So then, in fact, you are more or less in the case of Laplace operator with Dirichlet boundary condition. Okay, so somehow you see this is really what I told you in the beginning. You have this exponential kx1, which is somehow the largest growth you are allowing in your computations and to get estimates. Okay, so anyway, in here, both terms are zero, so you can tell me, okay, this is not important. We will see later that, in fact, it is important. So I want to stress a little bit this. But still, I mean, as soon as you have the above estimate, you see you have that the integral of d1 v hat of x1 psi prime square plus k minus psi prime square of v hat x1 psi prime square the x1 is less than a constant times, well, the constant is 1, sorry, w hat x1 psi prime square the x1 and 0. Okay, so I think that my time is almost off. So let me just tell you that this by Poincaré, you get 1 plus k minus psi prime v hat x1 psi prime square dx1 less than w hat. On w hat, we have an estimate with k plus psi prime coming from the previous estimate, right? So we have f hat x1 psi prime square dx1 plus k plus psi prime of gn hat of psi prime square. And so then, okay, maybe I keep this one. So if I keep this one, it means that probably I should divide by 2. And so then you can integrate in psi prime, get estimates in L2 and x1, 0, 1, and L2 psi prime. So let me blah, blah, blah. Sorry. Which will be L2 psi prime RD minus 1 with values, okay, with some weight function here. So, okay, of the functions V hat and F hat. Okay, and then you do Parseval's identity. And you get the result. Okay. So I will not give all the details. Okay, I just wanted to show you how to get estimates when we have this system. So once we have the estimate, I mean, you have the estimates for each psi prime. So then you just play with this and with Parseval's identity and you get the result. Okay, so I will stop here because my time is off. So next time I will try to explain what is the use of these Carleman estimates, what we can do with that, and try to generalize this approach to other settings. Thank you.
Thank you, Sylvain. So now I ask the audience, though, if you have a question, you can ask Professor Sylvain.
So I have one question in the Carleman estimate. What is the role of that the parameter k in the Carleman estimate?
What's the rule?
Yeah.
Well, this is something I'm trying to explain next time. So you see in this estimate here, you have, you know explicitly how everything depends on k, right? And k can be made arbitrarily large. Okay, so in fact, in some sense, k quantifies the level of instability that you want to consider. So what I claim is that embedded into this inequality, you have a unique continuation property for the Laplace operator, simply because k can be made arbitrarily large. Okay, so I will explain it precisely next time, tomorrow.
Thank you.
Okay, and you will see also that it will help to get similar results in the presence of lower order terms. Right, so somehow, sometimes it is said that k quantifies the compactness of lower order terms. Okay, but this is not completely standard, and this is not completely true either. So, but in some sense, this is what it does. So, if you add some lower order terms in your Laplace operator, with these Carleman parameters, you will not see the difference.
Thank you. Thank you.
Hello. Can you please show the second last slide? I have, because if you show, then only I can ask you.
So the second last slide, well, I don't know what it means, because for me it's continuous.
Yes, yes. Just go a little bit below.
Yes.
Yeah, and then estimates of V hat. So
Yeah.
there should be one more term, which I think you have subsumed. Am I correct? Which is less than or equal to from the previous estimate? Or no?
No, this is, well, this one here is an identity. So you are here at this step.
Yes, and the next step?
So the next step, it comes with the plus, right?
Yes, yes.
So
Okay.
I'm just developing, and there is a cross product.
Yeah, okay.
And that's all I'm doing. So this is really an identity here.
Okay, no problem.
I have a question concerning the splitting that you perform in the operator. What happens if you consider, for example, no longer direct boundary condition at 0 at 1, but Newman boundary conditions, and instead just in one of the ends the direct boundary condition? You can also perform this splitting of the operator, of the conjugate operator.
Well, you see the splitting is inside, in fact. So the splitting, you can always do that. Okay, the splitting is in omega, not on the boundary. Of course, there are boundary conditions on which you see things better. And so I don't know precisely what kind of boundary conditions you have in mind, but if it is Neumann on both sides, indeed, you need to be slightly more careful. So that proof will not work directly. But the mechanisms of instabilities are, in fact, they are the same, because they are related to what's inside, not on the boundary. Does it answer your question?
Yes, yes. In that case, you have to deal with the, I think, with the operator, the full operator, and you can do it some similar computation as you perform. Okay, thank you.
Okay, So if there is no more questions, let us thank Sylvain again.
Thank you.